Next up on stage we have our final speaker for tonight, our changemaker, Anna Halepaska, a Ph.D. student in the School of Architecture under the supervision of Professor Salmaan Craig. With Anna, we are going to take a look at our architectural marvels of the past to help find solutions to our heat recovery problems of the future.
In 1891, these drawings were sent to the Board of Governors of the former Royal Victoria Hospital. If you grew up in Montreal, you're probably already familiar with the Royal Vic. But if you're not, it's this lovely building just up the hill. The drawings, like this one, showed the architect's plans for heating and ventilating the patient wards. Here's what he proposes. Cool air would be brought into the basement and preheated using a series of hot water pipes. The warm air would then be delivered up to the wards through a series of supply flues embedded in the walls. Once it had circulated over the patients, it would be collected up into the attic through another set of flues, and finally exhausted via a central chimney. Now remember, this is the 1890s, so it's before the widespread use of mechanical fans. Instead, everything is powered by the natural buoyancy of warm air rising through the flues and out the chimney. That's pretty neat, right? That's not what they built. The architect, Henry Saxon Snell, was British. He was working remotely from his office in London via letter. So the Board of Governors hired a group of local architects and engineers to help realize his drawings on the ground here in Montreal. But when those local experts saw Snell's plans for heating and ventilating, they objected, relatively strenuously by Victorian standards. The plans were, and I quote, condemned as being quite unsuitable for this climate. Here's what those local experts designed instead. Cool air is still brought into the basement, heated using a series of hot water pipes, and delivered up to the wards through supply flues. But instead of being exhausted via the attic, the stale air is brought back down to the basement. It's collected into this long extraction trunk which ran the length of the basement, leading to that same central exhaust chimney. Why? Why draw air downwards? What makes this plan more suitable for Canadian climate? It's actually an answer to a common Canadian problem. Frozen pipes. In Snell's plan, on the right, cold air is introduced directly to the hot water pipes, which would have condensed and frozen in sub-zero weather. And surprisingly today, that feels pretty common again, despite the rest of this winter. That would halt operation and risk patient lives. So the local experts used exhaust energy to keep that from happening. On its way to the exhaust chimney, the warm exhaust air would pass its heat to the brick walls of that long extraction trunk. Those walls would then pass their heat to the cool incoming air in the basement. So that air is preheated before it reaches the radiators, and using energy that otherwise just would have been lost to the atmosphere with the ventilation stream. Now, remember, there's no fans involved. Everything is powered by the buoyancy of that exhaust air. So to make up for that lost energy that's transferred to the basement, the smoke flue for the central furnace, which was already being used to heat the hot water for the pipes, was run through the same chimney as the exhaust, boosting the flow with another source of waste heat. Now, if there are any mechanical engineers in the room, you may have realized that's heat recovery ventilation by Canadian engineers in the 1890s, before widespread electrification or mechanical fans. We do estimate that the efficiency was probably low due to low performance materials of the time, but it didn't need to be much. Unlike modern high-performance heat recovery ventilation, this innovation wasn't focused on energy efficiency, really. It was just focused on keeping the pipes from freezing and maintaining a healthy ventilation rate for the hospital. And importantly, we've simulated that that scheme would have provided a ventilation rate of between 40 to 60 liters per second per person, or between 3 and 4 fresh air changes per hour. To put that in context, our current ASHRAE standard for patient rooms in hospitals is 4 air changes per hour. And they're doing this with one of the earliest examples of heat recovery known today. I mean, if you've thought about heat recovery ventilation, and I realize that most of you probably haven't, you assume it's a 20th century invention, that it's reliant on mechanical fans and ducts and compact modern heat exchangers. But notably, and really inspirationally for an architect like me, the heat exchanger at the Royal Vic isn't a compact device. It's not tucked away in a mechanical room or an attic somewhere. It's the long brick wall of the extraction trunk. It's this spatial sequence of cold basement and warm exhaust. It's embedded into the architecture itself. So, if that ventilation system is so inspirational, let's be inspired by it. What I've done is reconfigure that natural heat recovery loop for a modern building. It starts with these 3 spaces. They share a ventilation stream that's driven by buoyancy from the high vent in the final space. The flow remains stable so long as the buoyancy in that space is enough to overcome the resistance from the previous ones. The second room is actively heated, but the other ones aren't. That generates a cascade of temperatures as energy is carried into adjacent spaces by the ventilation stream. So you have a cold first space, a hot second space, and a warm third space. But Anna, that's not heat recovery. Look at all the energy being lost from the exhaust. Like the Royal Vic, you fold the building around itself to bring the warm intake, or the warm exhaust and cool intake together. Heat is recovered from that exhaust, transferred to the intake across the shared partition. Again, no ducts, no fans, just a careful spatial arrangement and the fabric of the architecture. And this is only one potential spatial configuration. There are many, many, many others. In my research, I use physical experiments to characterize the thermal performance of those natural heat recovery loops. The models are fairly small, around 1 meter high, but the dimensions and heat input are scaled on fluid dynamics criteria, so the small-scale flow mirrors that of a full-scale building. That way we can make both qualitative and quantitative observations about its behavior. They visualize the flow using a technique called background-oriented Schlieren. I realize that series of words sounds wild. It's related to digital image correlation, if that's more familiar. But essentially, it allows me to visualize heat-driven flows that would otherwise be invisible to the naked eye. So, for example, the visualization on the left is a hot plate that's just a few degrees above ambient temperature. And the visualization on the right is that same hot plate at 30 degrees above ambient temperature. You can see the difference in the flow behavior. With all that primed, here's the proof of concept. It explores another spatial configuration that's closer to the original ventilation loop at the Royal Vic. It has all the same pieces. There's an intake, a basement, a heated space, an exhaust trunk that's carrying air through the basement, which will be hot if there is no heat recovery, and will cool down as heat is recovered, and a chimney. Performed 2 versions of the visualization. The first is a control, where the space carrying the exhaust through the basement is insulated. If we zoom in on that basement space, you can see that there's really no visible plumes in the basement, because there's no significant heat transfer happening between the exhaust stream and the intake. In the second version of the experiment, that space operates like a heat exchanger. This time there are visible plumes, as heat is being transferred from the warm exhaust to the cool intake. Nevertheless, despite the loss of driving energy from the exhaust, which is pulling air through the loop, the exhaust plume on the top right remains stable. And really, the smoking gun, as it were, for heat recovery is the temperature of those exhaust plumes. In the control, the temperature of the exhaust is comparable to the warmest point in the system. All of that energy is just being vented out into the atmosphere. But in the experiment, the temperature of the exhaust is significantly reduced because all of that energy is being recovered back into the system. We measured a heat recovery efficiency of about 38% for the small-scale model, but other and full-scale configurations could reach up to 50% efficiency, just with a careful spatial arrangement. So that's all really cool, at least in my opinion, and hopefully now in your opinion too. But why is it important? Why do we care about a ventilation system from the 1890s or how it could inspire a building today? Put very simply, we need to build better buildings today. Architects like me have become accustomed to using mechanical systems to heat, cool, and ventilate our buildings, no matter how they're designed or where they're located. And that sounds great, right? We can design whatever we want, like a glass skyscraper in a desert, and then turn around and ask a mechanical engineer to make it comfortable. And in hindsight, I'm really sorry for all the stress that we've put you through. Because that design paradigm is also horribly unsustainable. It doesn't just take an enormous amount of energy to heat and cool and ventilate buildings, around 60% of household energy use on average. It also takes an enormous amount of infrastructure. Think about all the fans, compressors, refrigerants, and the miles of supply and return ductwork. When we design a thermally arbitrary building, like what's essentially a greenhouse meant to keep things warm in the hottest climate in the world, we compensate by massively oversizing our infrastructure. And that infrastructure is becoming an increasingly significant source of emissions, up to 20% of a building's total embodied carbon, according to recent studies. Now, I'm not advocating for completely obviating mechanical systems. No solution is one size fits all, but I want to emphasize that that includes mechanical systems. By prioritizing passive strategies for thermal regulation and ventilation, we should be able to minimize the times when we need those active systems, and hopefully prevent them and their emissions from becoming oversized. Natural heat recovery loops are just one example of how those passive strategies can inform better building designs. Exhaust heat recovery and natural ventilation are programmed into the fabric of the architecture. So all you need is a heat source, which could be solar or, in a well-insulated building, just the waste heat from occupants like you and me. And speaking of occupants, some of you may have realized that in order for that heat recovery loop to work, all of the rooms in the building can't be the same temperature. Otherwise, you wouldn't get heat transfer. And that's really contrary to our modern Western idea of thermal comfort, right? We have this idea that every room in every building in every climate should be 21 Celsius. And hopefully when I say it that way, you sort of realize how absurd that sounds. So that thermal variety might seem like a catch, but it's actually another vital part of designing better buildings. Exposure to thermal variety makes occupants more thermally resilient, meaning they're at less risk of thermal stress during peak heating and cooling events, and they're comfortable over wider temperature ranges. Studies show that as little of 2 degrees of indoor thermal variation is enough to notably improve our metabolic rate, putting us at less risk of thermal stress and improving our cardiovascular function. Moreover, studies show that occupants in naturally ventilated buildings, where temperatures are allowed to vary about 4 degrees on either side of a daily mean, are overwhelmingly more satisfied with their thermal environment than occupants in buildings with strict mechanical control. Plus, reduced set points for heating and cooling means reduced energy demand for heating and cooling. So really, it's all a win-win. And finally, we shouldn't just care about one ventilation system from the 1890s. We should care about a lot of them. It should come as no surprise that as we're searching for building strategies which use less energy, we can be inspired by strategies from a time when energy was less readily available. But it is a surprise, or at least it really was for me. I'm not from Montreal. I had no idea the Royal Vic existed before I moved here 3 years ago. I certainly didn't start my PhD interested in how it was ventilated, or really in 19th century ventilation at all. I mean, who would? Really only got involved with it because my supervisor and our collaborator had been researching the project for years and needed an extra hand. But as I delved into the historic drawings and letters, I was enraptured. Here is this fantastic innovation just up the hill, sitting forgotten in a basement. We're so focused recently on making our current building technology better, more efficient, less carbon intensive. But in doing that, we shouldn't forget the centuries of human innovation and experimentation that is embedded in historic buildings and in local and traditional knowledge and practices, which might suggest a different solution. The Royal Vic is only one story. There are so many left to write. Thank you.